Hey, so this is chapter 4A, and this is where we discuss the differences in ionic and covalent bonding. Now, both classes we had gone back and we had reviewed chapter 3C, and that was at the end of the other video where we talked about balancing charges. So we had like Na plus and we had chlorine minus, and we talked about how when those come together it makes NaCl. Or if you have something like Na plus and PO4 minus 3, you're going to end up needing 3 sodiums and just 1 PO4. So this is all in the other section, but we did review all of that. So you might go back and watch the end of the other video if you don't remember doing any of that. Okay, so if we're going to be looking at ionic and covalent bonding, there's a lot of general information that you want to know. And the way I went about approaching is I just kind of had a big section where we just have a lot of fill in the blanks and we talk about things for a while. And then we get into naming compounds. Got some DeWitt videos. Crash course is a little bit deeper. But this basically does a good comparison of ionic versus covalent bonding. So we're going to start with this ionic bonding right here. And again, we got all kinds of videos in here. And don't forget, here's the Newton homework that's associated with that. So the first thing we want to point out is that ionic bonding is considered to be a stronger bond than a covalent bond. So the example in class was if you had 2 really strong magnets with each other, and you're trying to pull them apart, you know, the really strong ones, versus like having a rubber band and you pull on it until it breaks. So the covalent like breaks more easily. And I've had someone ask me about network covalent bonding before. You're not going to see it in Gen Chem. You'll see it in like geology and some other classes. That's like a special case covalent where the covalent bonds are building on top of each other and they make this kind of super molecule that's super strong. So that's the one case of a word where you'd find covalent being stronger than ionic. But in Gen Chem, we see ionic bonding is stronger than covalent bonding. All right, so an ionic bond occurs between a metal and a non-metal. And if we look at our periodic chart, and I'm just kind of going to draw a generic little picture up here, but if we look at the periodic chart, remember you've got those stair steps that happen over here. All of these sides, all the guys on that side's a metal, and everything over here is a non-metal. We've talked about that a few times. So when you're crossing the line and you're doing bonding, that's ionic. If you're staying within this section, if you're within this, that's going to be covalent. So if you need a picture of reference, anything that crosses over the line is ionic. So it's between a metal and a non-metal. Now, on our periodic chart, everything on this periodic chart is listed as neutral. So the neutral stuff's not really attracted to each other, but some elements have higher energy. I kind of was talking about it in terms of currency. So it's like some really would like an electron, and they basically have a good energy currency that they'll give up a lot of energy to get that electron, and they'll give it to the other atom that's giving up the electron. So the idea is that first thing that has to happen is you have to have an electron transfer happen. Oops. So you've got this transfer that has to happen. Once they transfer, remember electrons are negative, and they're going to go from one atom to the other. You're going to have one atom losing and one atom gaining electrons. So it's going to have a positive negative situation, which is great. We all know what happens when positive and negatives get near each other. So some atoms prefer just to lose like 1, like sodium. He prefers just to lose 1 electron. He'll go +1, whereas like calcium, he'd like to lose 2 because of the columns that they're in. And then chlorine, he prefers to gain 1. And then like nitrogen prefers to gain 3. So these preferences are based on which columns they're in. If you remember, like this column is +1, this column is +2, aluminum is +3, and then we jump over to nitrogen, -3, oxygen is -2, the whole column, until you get to the stair steps. Fluorine is -1, and then you have the neutral noble gases. So the idea is that these noble gases that are sitting over here, they are super stable. And everyone wishes that they could be like the noble gases. And that's what's really happening with these. When we say like this column right here goes negative, we're saying he's gaining an electron. So here's fluorine right here. He's got 7 electrons on the outer shell, the valence electrons. He's got 7 of them. He's missing this spot right here. If he could just get someone here, then he would be like a noble gas. And this is a very low energy state, and we always love to be in low energy states. So he's got a lot of energy that he's giving up to someone else if someone else would just give him an electron. So if there's someone else who has an electron, he might just say, hey, give me your electron and I'll give you a whole lot of energy. That kind of situation. So it's going to lose or gain electrons until it's reached an octet or 8 electrons. That's what this last column has. It has an octet, which is 8. And again, 1, 2, 3, 4, 5, 6, 7. And then this column, they've got the extra electrons, so that would be 8 electrons. Everyone wants to be like him. There are exceptions, but everyone wants to be at 8. So once you have your cation and your anion, because the anion took the cation's electron, once they're formed, everyone knows opposites attract. Positives, negatives, like magnets, are attracted to each other. So we use a fancy word, and it's called electrostatic, but that just means that positives and negatives are attracted to each other. So you understand that concept. And it happens between a cation, again, which is positive, and an anion, which is negative. Or it could be positive 2, negative 3, just whatever it is. But that's the negative and that's the positive. So we understand that. But, you know, in chemistry, we like to give things labels and laws. So Coulomb's law right here is the thing that tells us, oh, so when you have an electrostatic attraction, it's got some things it depends on. It depends on the amount of charge that the ions contain as well as their distance apart. So this does make sense. I'm going to draw this picture up here. So say you've got your refrigerator and you're getting those magnets, and you know, you can buy those really, really fancy magnets that are like really small, and you can put a paper on there and like it's not going to move if a tornado goes through. And then they got the other magnets where the second you put it on, that paper just starts sliding down and you're like, argh, it won't let me grab it. Well, you're going to have to imagine that guy is sliding down because of the magnet not being very strong. So it would make sense that the amount of charge the ions have is going to affect how well they attract, positive and negative attract, so that's going to affect things, but also their distance apart. So if we have our atom right here, and we've got some electrons right here, we'll make it a cation. And then if we have another atom, and we're going to give him his 8 because he's super happy. 1, 2, 3, 4, 5, 6, 7, 8. So you guys all know this too. If your magnets or your poles of your magnets are really far apart, they're not going to sense each other. But if you hold a magnet in your hand and you start to move them towards each other, there's a point at which you can feel the tug, and then it goes really fast. So they want to be close enough so that they have the strongest interaction, but with atoms you can get too close. So at the moment, this guy's electrons right here are attracted to his nucleus, and this guy's electrons can be attracted to that nucleus. So it's like a positive negative effect, plus the ions are attracted. So that's good, but you can be at a place where you have too much. So if we take this atom and we try to put him here, now we have a problem with our nucleuses. Do you see how our nucleuses, which are both positive, are now really close to each other? So nucleuses don't I guess the word would, they don't feel each other at very far distances, but there's a point at which this is too close. So like that may be just right. That's not right. That's not right. There's like a certain point. And it's atom specific. It's going to depend on how much charge they have and how far apart they are as to if they make the ion. So that all makes sense, hopefully. They also combine in the simplest ratio that will allow the overall charge to be neutral. So ionic things, make sure they're neutral. So if you have Fe plus 2 and it's combined with O minus 2, the ratio should be 1 to 1, not 2 to 2. Also, we call a bonded cation and an anion a compound. So you can kind of use the word compounds synonymously with ionic. So compounds have ionic bonding, synonymous. And remember, this is pulling in something from a way back. Compounds are made up of, if you have 1 mole of compound, they are made up of formula units. And there are this many formula units in a mole of a compound. Also, we have some properties over here. So they are soluble in water. You know this too. You know, like if you take salt and you put it in water, it dissolves. And even if you have salt that has like other salts in it, like if you have one like Himalayan salt or some other kind of a salt that has extra things in it, they still dissolve in water. The whole salt dissolves in water. They also have high melting and boiling points. This just means that they are solids. Have you ever tried to melt salts? Because it takes so much heat to melt it. It'd be really hard to do it just like on a stove. So they're solids. Most ionic things are solids. Now they do dissolve in water. And when they dissolve in water, they conduct electricity. And I'm kind of previewing something, but water is really funny. This is water. And he has kind of sort of positive and a kind of sort of negative area to him in the water. And again, this is previewing. This would be something you'd learn next time. But interestingly, when you put something in like NaCl, the NAs break apart from the Cls and they kind of congregate where the positive Na is near the negative part of the water. And the reason I'm even mentioning this is because we're talking about conducting electricity. If you get an electron in here, he's going to be like, whoa, oh, don't want to go near him, whoa. And they move so well in water, and they do conduct electricity. And here's our picture over here. So we call this a lattice type of shape, but all of these guys make these kind of cubic shapes. So I have an NaCl example right here, but if you had something that was like 1 to 2, you would have him and then like 2 things, and like the ratios would be different. Like the numbers of, you'd have less purples and you'd have more greens, but the purples would be like bigger and stuff. So every time though, you're going to have this cubic shape. You can have a layered upon layered upon layered upon layered cubic shape. So just really big. This is why our salt looks nice and cubic, and it has fracture points and things like that. So that's the look of him. It's very different from the next thing we're going to talk about, which is covalent. We do a lot of comparing and contrasting. So for a covalent molecule, that's between a non-metal and a non-metal. Remember at the chart, that's this section. Whenever you have 2 non-metals in here, bonding within this section is a covalent. So one or both atoms tend to lend electrons, and the electrons are shared, not transferred. So we don't have any positive or negatives. It's possible because of orbital overlap. So if you remember, we have these atoms, and the electrons are moving, and then notice that that overall shape looks like an S shape. So if I have another guy, and his electrons are moving, and he has an S shape. Let's say that this left one has an electron in it and the right one has an electron in it, and they both need one more to be completely filled, and then they'd be happy. Orbital overlap is where they get close enough that they can jump into each other's fields, basically. And so this guy on the left, the one that's down can jump over here, and then this one can jump over here, and they basically can move in between the two and make like this big space of electrons moving. Each atom will then feel like it has 2 total. So the green atom guy feels like he's got 2, and the red atom guy feels like he has 2. It's like a weird way of doubling the number of electrons you have without actually adding electrons. So it's orbital overlap. Again, the orbitals are the shapes that the electrons get in when they move. And they make something called a covalent bond. Notice I don't have them on top of each other because we got that nucleus issue where if you have them directly on top of each other, the nucleuses are going to repel. So there's a certain distance that is lowest energy. So it might be the way I have it, or it might be even a little closer, or maybe a little far away, but there's a certain distance that's lowest energy, and that's what's perfect for the bond. So you could imagine that for that guy, that's a good bond distance, but like if I have something really big with just 1 electron in it, and something really small with just 1 electron in it, and it just kind of depends on the atom, right? But for me to have a good overlap, I might have to bring him in a little more than I brought that other one in. So it's unique. The atoms move to this, whatever this perfect distance is, it's unique, very unique to each covalent bond, and it's called a bond distance or length. And we have charts and charts of these. So it's just saying like a carbon-carbon bond, that distance is not the same as like a carbon-nitrogen bond. It's unique. They're going to be close, but I mean, it's not the same distance. Interestingly, both atoms will act as though the shared electrons are their own, and it counts towards their own total of 8. And note that they are motivated to share, kind of for the same reason. They want their valence electron count to be an octet or 8. Just like before, they wanted it to be 8. So they still want to be like a noble gas. They're just sharing to make that happen. And there are exceptions to that rule of 8 we'll learn about next time. These are called, like earlier, the ionic compounds are called the ionics are called compounds. These are called molecular or molecular bondings. Remember that 1 mole of a molecule is this many molecules. Also notice that most covalent molecules are not soluble in water. Think of like butter and oil and stuff like that. Some are, but most are not, and they do not conduct electricity in any state. Note that they do have their own unique shape, and they could ultimately combine into large shapes with other molecules. You get DNA, proteins, etc. And these are just some of the examples. If you've had any chemistry before, most people will remember names like trigonal planar, trigonal pyramidal, but they look like this. So you can see how this looks very different from the guy up here in the corner. So the guy in the corner, you just have these cubic shapes where they all layer up on top of each other. These guys, they have really unique shapes, and that's why we're going to focus on all of those next time. As a little note, we're going to do the rest of 4.2 at the very end of the chapter. So either at the end of next time or the time after that. All right, so now that you know covalent and ionic, we are going to touch on naming compounds. Here's Dr. Bean's video. She goes through all of these. This is one of those subjects where, in a way, it'd be nice to just teach like one type of name a week. I think people would keep it up with it better. But the way our book does it, it does it kind of all at once. So we're going to start with ionic naming, and you'll notice that this section, and this, like that's all then the ionic naming. And then we have a little bitty covalent and a little bit of hydrate. So the covalents don't have a lot of naming options, but there are a lot of naming options for ionics. I also gave out a flowchart in class, and it's in color, and it starts with something along the lines of, is the first element an alkali, alkaline, or aluminum? And if you'll notice, K is in that category. So if you said yes, you would go in this direction. And then there's another question. So this is a flowchart that would like help you with different namings and things. And there's a no answer. So it's in your notes that you can check out those flowcharts. And a little note, we mentioned about this cross and drop method to help you convert a name to symbols. We are mostly going to take our symbols and turn them into names, but cross and drop is where you have like Ca plus 2 and Cl2 minus, and you cross and drop. Like that's how you get to the Ca and the Cl and their charges. All right, so we're going to keep going on. So in this category where you have a metal of those types and a nonmetal, you name it with just the element first. Then you shorten the name and do "-ide." And most of the time the shortened name makes sense, but there's a few cases that aren't expected. Sulfur doesn't shorten most of the time. It does sometimes. And then oxygen shortens a whole lot. A lot of times that just shortens to that. So sometimes that's sulfur, and sometimes it's sulf, and sometimes it's sulfur. So those are kind of two of the weird ones. You can't always guess what they're going to do. But if you have a K, that's potassium, and a Cl, that's chlorine. So we're going to name it potassium chloride. And then the next one, magnesium. Again, that's an alkaline metal. Chlorine is our nonmetal, so magnesium chloride. Notice that we are not using any prefixes. No dies, tries, or anything. It's because if I say magnesium chloride, magnesium always goes +2, chlorine always goes -1. And because of that, it always combines in a certain ratio, 2 to 1. 2 of these guys and 1 of these guys. So I don't have to use a prefix to tell you how many they are, because they only ever form certain charges. So no prefixes until you get all the way to covalent bonding. And then here's our next one. This is the same category, but a polyatomic ion. Now you have a list of polyatomic ions that you were given. It's words like NO3, PO4. You will be able to use them on the test. SO4, sulfates, things like this. So we just find him on the chart. He will have a charge listed, and you just write that name down. So potassium, so that's the plus, and nitrate is the minus. And the next one, aluminum nitrate. Again, we know that aluminum always goes +3. He's -1. Again, you'd get that off the chart. I just know him, but you'll see it on the chart. He's -1. And so we needed 3 of them. And then because the other guy was neutral, or just 1, you only needed 1 of him. So aluminum nitrate, you just state the first element, just like before, and then you use the name of the group. And if you look on that flow chart, you'll see that the transition metals, they answer different questions, but you name them the same way as you name the earlier guys. So you name them similarly to here. You just also need a Roman numeral. So the reason we do this is because the transition metals can be more than one amount of positive. So iron might be +2 or it might be +3, and you have to tell me what it is. We don't use dies and tries to do that. We look at what the charge would be. So if you like the cross and drop, so if that's a 2 and that's a 1, that means that iron's charge is +2 and chlorine is -1. So that would make this iron 2 chloride. Make sure you're using capital I's, Roman numerals for that. Then here, this is iron 3 chloride, because again, 3 plus -1, when you copy it across, you end up with 3 Roman numerals. Here's another situation of doing it. You can see the 3 comes up and the 2 goes over. I also have the math way of doing it. So if you like it with the math, you could say that there's 2 irons -6, and that comes from there being 2 and 3. So -6 equals 0. 2 irons equals 6. So again, 2 irons equals 6. So 1 iron is 3. So this is really important. These Roman numerals are for one of the elements. So if you have 2, you have to convert it down and make sure that it only is for one of the elements. I've got a few more here. This one was incorrect, and we rephrased it as MnCO3, so fix him. So this is manganese, and go ahead and say the second part, carbonate, just like before, carbonate. And then we have to figure out the charges. If carbonate is -2, and you would see that on the polyatomic lists, and there's only 1 magnesium, that means that magnesium is +2. And that's why our Roman numeral is 2. And then over here, our nitrate group is this -1, and that's because of the polyatomic ion chart tells us that. There's 3 of them, so that's -3, and so this is +3. So magnesium 3 nitrate. Now, if you're at a point and you just want to stop thinking about stuff for a while, you can stop that, and you can work that homework and make sure you've got those down really, really good. The next category is acids, and there's 3 ways to name acids. So if you have H with an element, you're going to name it using hydro, ic, and acid. If you have H with an 8 polyatomic ion, if you look at your polyatomic list, most of them are 8s. They end in 8s, like nitrate, phosphate, perchlorate, chlorate, acetate. They all end with that 8. And that one gets an ic acid with no prefix, nothing. Whereas if you have one that ends in ite, and there's like 4 of them on there on your list, those become us acids. So if we do these 3, so we have hydrosulfuric acid, hydrochloric acid. So this is one case where the sulfur doesn't shorten. Then we have our 8 polyatomic ions. So we have nitrate, perchlorate. You see how those have 8s? That's the names of these groups, again, from the polyatomic ion list. The 8 ions become ic. So this is nitric acid, and this is perchloric acid. So the 8 becomes ic. Again, the 8 becomes ic. And you add the word acid. All these have the word acid added. And then last but not least, we have our ite, and ites become us's. So nitrous acid and chlorous acid. Then we have our covalent naming. Now this is the one that's easy. Everyone loves to do these. And everything for the Lewis structures, this is the kind of naming we're going to be doing. So you should expect like dies and tries and everything on Lewis structures. Now the key with this is that everything gets a prefix, and someone has to tell you how many there are. Like you can't halfway guess it. You have to know exactly how many atoms of which type you have that number of atoms. So they all get a prefix except for in one case, and it's for when you have one of the first atoms, you can skip mono. So like here's a case of having one of the first atoms. You don't have to have the mono prefix. It's just nitrogen monoxide, which probably sounds to you like carbon monoxide. So they are like written the same way, and they have those same kinds of ratios. Then we have dinitrogen monoxide because of the 2 di, and then we have NO2, which is nitrogen dioxide. As a note, in lab, in Gen Chem, hydrates can be very easy to work with. This won't be on the test, but it's in lab, and it's going to be in your lab today. So we already talked about how to name him and him. So this first one is copper, and it's a sulfate. That's a sulfate group. And then sulfates are -2, so that means that since there's only one copper, he has to be +2. So that's copper 2 sulfate. You write that here, and then to make it a hydrate, use the same prefixes. So penta, there's the same prefixes all in this line right here. Pentahydrate. You always use that word hydrate after. So then for the second one, magnesium sulfate, hepta, because there's 7, hydrate. So this is just like the method. You definitely have to practice these. There's practicing at the end of the book. There's practicing in Newton. There's a ton of practice for you for these guys. And I know everyone is ready to stop at that point, but we have just a little bit we're going to touch on, and it was just through finishing out this page. So we talked about valence being the electrons in the highest occupied energy level. So like if this is your positive nucleus, you've got your electrons here, and you've got electrons out here. Well, the ones on the outside are the ones that are the valence electrons, and they call it the highest occupied energy level because the further out you go, it's higher energy. But it just means the most out electrons. They're the ones that do all the chemistry, all the sharing, all the transferring. And just remember about counting the columns again on your periodic chart. This column has 1 valence electron. This has 2, 3, 4, 5, 6, 7, 8. And that's our noble gases is right there. And last but not least, Lewis dot structures. This is the beginning of a topic that we'll be continuing on. You use dots, and you put them around the element as single dots before you pair them. Ionic bonding are cations to anions, and they have charges, but they don't have any lines for the bonding. Whereas the covalent ones, they do have that line for the bonding. And an overall charge, it's placed as a superscript outside the bracket. So I'll show you what you do. So like if you zoom in here for the hydrogen, right there, see how they have all those different positions? So you could put an electron here, or here, or here, or here. None of those are wrong. That's all fine. We can call him right there. He has 1 because he's right here on the chart. Now magnesium's in this column, so he has 2. 1, 2. Or I could have done it in other places, but they have to be separated. And then my chlorine, he is right here. So he has 1, 2, 3, 4, 5, 6, 7. Now my fluorine, he's also in this category. He's up here, but he has the negative. So he's F. 1, 2, 3, 4, 5, 6, 7, 8. Give him brackets and his charge. That's what it was talking about right here, about a superscript outside of the brackets around the structure. This. And you may want to pause it and practice the last ones on your own. I'm going to go ahead and do them. Notice sometimes I'm starting in different places. It's okay. Now that calcium, look, he lost his 2 electrons. So I could write it like that. Or you can also say, okay, so calcium, if you look at your periodic chart and where calcium is, he's not that far from a noble gas. And I have seen some people go ahead and say, okay, well, that's like argon. And they'll say that's equivalent to saying Ar. So I've seen people also do it like this. Generally do it like this, but be aware that really what that means is that he now has 8 valence electrons because he lost that outermost electron. All right, so that's the end of this section. Just need to do a lot of practice.